Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. And previously, the previous module, we have looked at the bit error rate performance of a CDMA system. Today, let us look at the performance of a multi-user CDMA wireless communication system. So, what we are trying to look at today is a multi-user CDMA scenario. So, let us look at a multi-user CDMA scenario. So, for a simple illustration of this, consider two users, two CDMA users. So, we have basically what we have is we have two users whom we are going to denote by user 0 who has symbol A0 and code C0N. Then we have user 1 who has symbol A1 and code C1 of n. So, we have a two user CDMA scenario. We are starting with a simple two user CDMA scenario. We are considering user 0 who has symbol A0 and code C0 of n, and user 1 who has symbol A1 and code C1 of n. Okay. Therefore, the transmitted symbol xn in this scenario the transmitted symbol xn is given as xn equals A0 C0 n plus A1 C1 n, that is we have symbol of user 0 times code of user 0 plus symbol of user 1 times code of user 1. So, what we are doing is we are multiplying the symbol A0 with code C0 n of user 0. We are multiplying symbol A1 with code C1 n of user 1, and then we are taking the sum of these two components to generate the multi-user signal. So, this is the transmitted multi-user CDMA signal. This is the transmitted multi-user CDMA signal. The received signal, as we already know, the received signal y of n equals h times x of n plus W n, where h is the fading coefficient and W n is IID Gaussian noise samples with mean equal to 0 and variance equal to sigma square. So, we are saying the received system model y of n is equal to h times x of n plus W of n, where h is the fading channel coefficient, the Rayleigh fading channel coefficient, and W n are IID Gaussian noise samples with 0 mean and variance sigma square. This is the same system model that we have seen before in the previous module, but we are now extending it to a multi-user scenario. And now I am going to transmit are going to incorporate the multi-user transmitted signal, and I have yn equals h times a naught c naught n plus a1 c1 n plus w of n. So, this is the transmitted multi-user. So, this is basically my x n which I am substituting here, that is a naught c naught n plus a1 c1 n, and now I have the expression for y of n, and I can further write this as h a naught c naught n plus h a1 c1 n plus w of n. So, the received symbol y of n is given as h a naught c naught n plus h a1 c1 n plus w of n. Now, what we are going to do is we are going to correlate with the code c naught n of user 0 to extract the symbol a naught of user 0. This is similar to what we have been doing all along in a CDMA system. We said that at a CDMA receiver, we correlate, we perform the correlation operation with the code of the particular user to extract the symbol belonging to that particular user. Therefore, we are going to perform the correlation with the code 0. So, at the receiver, we correlate with code of user 0, and that gives us 1 over n summation of n y n c naught of n. This is the correlation, that is the element wise sum, element wise multiplication plus sum over all the chips and then dividing by n, which is equal to 1 over n summation over n h naught a naught c naught n plus h, I am sorry, is h a naught c naught n plus h a1 c1 n times c naught n plus 1 over n summation over n w n c naught of n, and this component 1 over n summation over n w n c naught of n, this is the noise component. We have already seen this in the previous module. We defined this as w tilde. W tilde is Gaussian noise with 0 mean and variance sigma square divided by n. This we have seen in the previous module. So, w tilde, so we have our, this is w tilde which is the noise component, which is Gaussian. Since it is a linear combination of Gaussian noise samples, the mean of this noise is equal to 0, and the variance, the interesting aspect of this is the variance is equal to sigma square divided by n, that is the variance of the noise is suppressed by a factor of n. Therefore, now simplifying this further, I have y of n is equal to h times a naught 1 over n summation over n c naught square n plus h times a1 1 over n summation over n c naught n times c1 n plus w tilde. Now, we have already looked at this component 1 over n summation over n c naught square of n, that we have seen is equal to 1. So, when we look at this component 1 over n summation over n C naught square of n. Since each C naught is plus or minus 1, C naught n is plus or minus 1, C naught square n is 1. So, this is 1 over n summation over n of 1, which is 1 over n times n, which is equal to 1. Therefore, this expression can be further simplified as y n is equal to h times a naught plus h times a 1 over n summation over n C naught n C 1 n plus w tilde. So, we have the final expression. Let me write this again. We have y of n equals h a naught plus h a 1 over n summation over n C naught n C 1 n plus w tilde. Out of these three components, we have seen two already. This first one h a naught is the signal component, the last one w tilde is the noise component, and this component in between, which is h a 1 summation 1 over n summation C naught n C 1 n is the multi-user interference component. This is a new component which arises in a CDMA system because of the simultaneous transmission to multiple users. This is a multi-user interference component. So, this is a new component in a CDMA system. This is the multi-user interference. This is the multi-user interference component, and this arises, we are going to denote this by MUI, which is for multi-user interference, and this arises in a CDMA system arises because of simultaneous transmission because of simultaneous transmission. So, the multi-user interference component in the CDMA system arises because of the simultaneous transmission to multiple users. Now, we would like to characterize the impact of this multi-user interference in terms of the power or in terms of the noise power or the interference power of this multi-user interference component, and let us look at that now. Now, for this, let us first look at this correlation component, that is 1 over n summation n C naught n C 1 n. Let us define that as R 0 1 equals sum 1 over n summation over n C naught n C 1 n. Now, we know that each C naught n comma C 1 n, each C naught n comma C 1 n equals plus or minus 1 with, because this is a random sequence, is a pseudo noise sequence of plus or minus 1, each C naught n C 1 n equals plus or minus 1 with probability half each, because these are PN sequences, each C naught n and C 1 n, each of the chips is either equal to plus 1 or minus 1 with probability half each. Therefore, now we want to compute the expected value of these chips. The expected value of C naught n equals half times plus 1 plus half times minus 1, which is equal to 0, and similarly expected value of C 1 n equal to 0. further, these two different chip sequences of user 0 and user 1 can be assumed to be independent. Further, C0n and C1n of user 0 and user 1 respectively can be assumed to be independent. Therefore, what we have is, we have, since they are independent, we have expected C0n C1n equals expected, since they are independent, the expectation of the product is the product of the expectations, which is expected value of C0n into expected value of C0n, and each of these quantities is 0. So, therefore, this is 0 into 0, which is equal to 0. Therefore, we have the expected value of the product, expected value of C0n times C1n is equal to 0, since the chip sequences C0n and C1n belonging to user 0 and user 1 respectively can be assumed to be independent. Therefore, we have expected value of R01 equals expected value of 1 over n summation over n C0n C1n equals 1 over n summation n expected value of C0n C1n, which is 1 over n summation over n of 0, which is equal to 0. So, what we have seen is that expected value of R01, which can be thought of as the cross correlation between the chip sequence C0n and C1n belonging to user 0 and 1 respectively, the cross correlation, the expected value of this cross correlation is 0. Now, let us look at the power of this cross correlation. Let us look at the expected value of R01 square. So, what is the power? The interference power depends on expected value of R01 square, which is equal to expected value of 1 over n summation over n C0n C1n times 1 over n times, that is product 1 over n summation m C0m C1m, which is equal to expected value of 1 over n square summation over n summation over m C0n C1n C0m C1m. Now, since the code sequences C0 and C1 are independent, I can further simplify this as 1 over n square 1 over n square expected value 1 over n square summation over n summation over m expected value of C0n C0m times expected value of C1n, that is, since the code sequence C0 and C1 are independent, I can write the expectation of the product as the product of the expectations expected C0n into C0m times expected value of C1n into C1 of m. Now, let us also assume now, since these these PN sequences are pseudo noise sequences, since PN sequences, since C naught n are PN sequences, we have expected C naught n, expected these different chips are independent if n is not equal to m. Therefore, expected C naught n into C naught m is expected C naught n into expected C naught m, and each of these expected values are 0. So, this is 0, but this occurs if n is not equal to m. So, if n is not equal to m, then expected value of C naught n times C naught m is equal to expected value of C naught n into expected value of C naught m, which is equal to 0 if n is not equal to m. However, if n is equal to m, we have expected value of C naught n into C naught m is equal to expected value of C naught square of n, since n is equal to m, which is equal to expected value of 1, since C naught square n is 1, each C naught n is plus or minus 1, which is equal to 1. Therefore, we have, in summary, we have expected value of C naught n into C naught m is equal to 1 if n is equal to m, 0 if n is not equal to m. Similarly, this also holds for the expected value of C1 n times C1 m, that is expected value of C1 n times C1 m is also equal to 1 if n is equal to m and it is equal to 0, otherwise that is if n is not equal to m. Therefore, the power of R01, that is expected value of R01 square, can now be simplified as one over n square summation over n summation over m expected value of C naught n C naught m times expected value of C1 n times C1 m. Now, we realize that these expected values survive only when n is equal to m, because they are 0 when n is not equal to m. So, summation over n, we have expected value of C naught square of n times expected value of C1 square of n, which is equal to each of these expected values of C naught square of n, C naught square of m are 1. So, this is 1 over n, 1 times 1, which is 1. Therefore, this is equal to 1 over n square summation of over n of 1, which is equal to 1 over n square times n, which is equal to 1, therefore, which is equal to 1 over n. Therefore, in summary, what we have is something interesting. We have expected R01 square equals 1 over n, that is the variance of R01, the cross correlation between the code sequence of user 0 and user 1. Expected value of R01 square equals 1 over n, which means it is inversely proportional to the code length n, right. So, therefore, now if we go back to our multi-user interference, now realize our multi-user interference, our MUI our multi-user interference is equal to HA1 R01. Therefore, the power in the multi-user interference, this interference power is expected value of magnitude H square, magnitude A1 square, magnitude R01 square, which is equal to magnitude H square times expected value of magnitude A1 square times expected value of magnitude R01 square, which is equal to magnitude H square, expected value of magnitude A1 square, expected value of magnitude A1 square is the power P1 of user 1, and expected value of magnitude R01 square equals 1 over n, which is what we already saw. Therefore, the multi-user interference power is given as magnitude H square times P1 power of user 1 times 1 over n. So, this is magnitude H square times P1 times 1 over n, which is equal to magnitude H square times P1 divided by n. Therefore, now going back to the signal model, if we look at this signal model in a CDMA system, we have the signal, interference and noise components. Therefore, the interference and the noise are the undesirable components. Therefore, we want to compute the signal to interference plus the signal to interference plus noise ratio, that is SINR. Normally, we look at the signal to noise power ratio, but in a CDMA system, since we have signal, multi-user interference and the noise, we look at the signal to the interference plus noise ratio. So, this is a new term for a CDMA system. So, arises in the context of this, arises in the context of because of the multi-user interference in CDMA, because of the simultaneous transmission to multiple users, that is equal to the signal power. This is what we have already seen in the previous module, that is magnitude H square P naught divided by the noise power, which we have again already seen in the previous module, that is sigma square divided by n, plus the new component, which is the interference component, which is magnitude H square P1 divided by n. Therefore, this is equal to, this can now be simplified as n times magnitude H square P naught divided by sigma square plus magnitude H square plus P1, where as we have seen previously, this n is the spreading gain and this P1 in the denominator is arising because of the multi-user interference. This is arising because of the multi-user interference. Therefore, let me write again the expression for this SINR. The SINR in this CDMA system, the SINR equals magnitude H square P naught times n, the spreading gain, divided by sigma square plus magnitude H square times P1. So, the SINR of this CDMA system in the presence of multi-user interference is n times magnitude H square times P naught divided by sigma square plus magnitude H square times P1. This can now be easily extended to a scenario with k plus 1 users. So, now consider a scenario with k plus 1 users, where we have 0, that is where we have users zero, 1 up to k plus 1. In this scenario, the SINR of this scenario will be given as n times magnitude h square times p naught divided by sigma square plus magnitude h square times summation over k equals capital K Pk, that is summation of the power, total power of all the users, where summation of k equal to 1 to k Pk is total power of all users other than user 0. So, this is in the denominator we have interference from total power of all users other than user 0. So, the SINR is n times magnitude h square times p naught, that is the signal power, divided by sigma square, that is the noise power, plus magnitude h square times summation k equal to 1 to capital K Pk, that is the multi-user interference from all the users other than user 0. So, this is the SINR of a multi-user CDMA system. Now, let us look at a simple example to understand this better. So, let us look at a simple example for this multi-user CDMA scenario. Let us consider a CDMA scenario. So, let us look at an example. Let us look at a multi-user CDMA example. Let us consider a scenario in which, consider a 2-user scenario with P naught equal to P1 equal to 15 dB, that is the power in dB, P naught dB equals P1 dB equals 15 dB. Similarly, let the noise power in dB sigma square dB equals 3 dB. Further, we have the code length n is equal to 256. We have the channel coefficient h is equal to 1 over square root of 2, the complex fading channel coefficient 1 over square root of 2 plus 1 over square root of 2j. Now, what we want to ask is what is the SINR, what is SINR of user 0. For this scenario, we want to find out what is the SINR of user 0, and the SINR of user 0 is given as, now let us convert first all these figures. We have P naught dB equals 15, which means 10 log 10 P naught equals 15, which implies my P naught is equal to 10 to the power of 1.5, which is equal to 31.62, which is also equal to P1, since P1 is also equal to 15 dB. We have sigma square in dB equals 3, which implies sigma square equals 10 to the power of 0.3 approximately equal to 2, because 3 dB is approximately equal to 2. We have the channel coefficient h equals 1 over square root of 2 plus 1 over square root of 2j, which implies magnitude of h square is equal to half plus half, which is equal to 1. Therefore, our SINR which is equal to magnitude of h square times n times P naught divided by sigma square plus magnitude of h square times P1. This is equal to, we have seen magnitude of h square is equal to 1 times n, which is the code length, which is equal to 256, times the power 0, which is 31.62, divided by sigma square, which is 3, plus magnitude of h square, that is 1, times P1, which is 31.62, which is equal to 233.81. Therefore, the SINR in dB equals 10 log to the base 10 233.81, which is equal to 23.68 dB. So, we can compute the SINR for this simple 2 user CDMA example, and we have seen that this SINR is 23.68 dB. So, this basically, this module basically summarizes the idea of the SINR, idea of the most importantly the idea of multi-user interference in a CDMA system, how to characterize the SINR, that is the signal to interference plus noise ratio in a multi-user CDMA scenario, and we have looked at a simple example to understand that this idea of SINR in a multi-user CDMA scenario. So, we are going to stop this module here. We are going to look at other aspects in the subsequent modules. Thank you very much.